Great. Well, first, it's a pleasure to speak at this conference honoring the science of Giorgio, and so this will be about the disordered model, which is not spin glasses. And Giorgio mentioned his work in the late 70s on the random field Ising model, and that inspired us with subsequent work that we did with Mathieu Tissier and then with Ivan Balog, and that's what I will discuss today with you. So the outline of my talk will be, well, first introduce the random field Ising model and more generally random field systems, the properties, and then what is the approach that Giorgio Parisi and Nicolas Solas proposed in the late 70s in terms of supersymmetry and its relation to dimensional reduction. Then I will discuss the metastable states that take place in the problem, avalanches, droplets, all things that are basically at the core of the failure of dimensional reduction and the breakdown, and the unfortunate breakdown of the beautiful supersymmetric Parisi-Solas construction, and discuss the ways to cure this problem. Then I will give some results, and in particular stress the fact that despite the fact that the construction seems impossible due to the multiplicity of metastable states, in fact, there is a range of dimensions, and in the ON model, we'll see of number of spin components for which actually the supersymmetry is still valid and dimensional reduction is valid, but this is in fairly high dimension. Then I will just briefly survey the way we handle this problem through the non-perturbative functional renormalization group, and finally give a physical interpretation of why there can be supersymmetry, dimensional reduction, while there is breakdown, and relate this to the properties, the large-scale properties of the avalanches. Okay, so that's the outline, and just to start with. So what is the random field Ising model? So it's prototypical disordered model, and it was introduced by Imre and Ma in 75, but probably before by Larkin. So the lattice hard spin version starts with a just ferromagnetic Ising model on a lattice, and just
all right.
Sorry, yeah, the connection was, I lost the connection. So I'll try to share and start again. Okay. So each spin is coupled to a quenched random field, which is independently, identically distributed, and with zero mean and some variance, and to avoid specific problems that it's generally taken as Gaussian or continuous distribution. And of course, one can think of the field theoretical description, on coarse grain view, where again, you have the bare part, the pure part, which is just the phi-4 theory, the equivalent of the Ising model. And then you have again the field, the scalar field, which is linearly coupled to a quenched random field, again, that we will take as Gaussian and with zero mean and some variance. And this model can be generalized, of course, to n component variables where the spins now are n vector, and the interactions have ON symmetry, and this is the random field ON model. But most of what I will discuss here today is really the Ising version. And it will also be about the equilibrium behavior. These systems have also interesting non-equilibrium behavior, but I will stick with equilibrium behavior. Okay, so whoops. So what is known about this this problem, since basically the work of Imre Ma is that To determine the existence of a transition, what counts is a competition between energies, I mean the interaction energy and the random field energy, rather than the usual competition between energy and entropy. And this basically reflects the fact that thermal fluctuations are irrelevant in that model compared to disorder-induced fluctuations, that is sample-to-sample fluctuations. And at the critical point, this can be made more precise in a sense that the equilibrium critical point is controlled by a zero temperature fixed point. So what this means is here, is the phase diagram, for instance, of the random field Ising model in above its lower critical dimension. And you have temperature axis, the disorder strength axis. And above here, there's a paramagnetic phase. And below here is a ferromagnetic phase. And there's a line of transition of critical point between the two phases. And if you look now, you turn this into a sketch of the renormalization group flow. So you see here 3 fixed points. You have the pure Ising fixed point at zero disorder here, and the disorder is relevant at this fixed point. You have the ordered fixed point for the ferromagnetic fixed point. And in fact, the whole transition line here is controlled by a zero temperature fixed point that you see here, which is the random field fixed point. So the whole critical behavior, again, is controlled by a zero temperature fixed point, meaning a zero renormalized temperature fixed point. But it also means that you can study directly, which is important, especially for numerical simulations. You can study directly the transition between paramagnetic here and ferromagnetic here by working at zero temperature. And this will be important discussing the Parisi-Sourlas construction. Now, what happens is that, okay, the temperature is irrelevant, but it flows, it has a specific exponent, which is an important one, the exponent theta, which is larger than zero. And temperature is irrelevant, but actually it's known to be dangerously irrelevant. I won't discuss this more, but it means essentially that the critical slowing down is very, very slow and is activated. It means that the thermal fluctuations are subdominant compared to the disorder-induced ones, but it are nonetheless anomalous, and other properties for relating exponents, violation of hyperscaling and stuff like this. Now, in those systems, there are 2 different pair correlation functions. One which is called the connected one, which is where the average, the bracket average, is the thermal average, and the oval line here is the average over the random field. And this guy has a power law behavior at the critical point with a new exponent, eta bar, and a kind of, a very a different behavior and a longer range behavior than the usual system with an exponent eta bar. And the other correlation function, which is called the connected correlation function, which is proportional to temperature, has the usual behavior as long distance in d minus 2 plus eta, where eta is the usual anomalous dimension of the field. So you see that this one, of course, has a slower decay. It's the one that dominates actually at long distance. And the fact that there's a change of exponents here, and in particular, for instance, at the upper critical dimension, where the 2 anomalous dimensions are 0, then the exponent theta is 2, and you see that this one has a difference of 2 compared to this one. And this makes, a displacement basically of the upper critical dimension for 4 for the usual Ising case to 6 to the random field case. Okay, so these are known properties of the random field model at equilibrium. Now, the idea of the Parisi-Sourlas supersymmetric approach is to start from, as I said, you can study the problem directly at zero temperature. And at zero temperature, the equilibrium is given by the ground state. And the ground state is a solution of the extremization equation of just the action here, for instance, I wrote, which is again the derivative of the phi-4 action minus a random field minus, if one wishes, an external magnetic field or an external source. Okay, and this is the quenched random field. So you want to build now generating functional of the correlation functions from the ground state of this solution, and this is simply implemented as usual by having some sort of pseudo partition function with an auxiliary source coupled to the field, and a delta functional that says that the field should be equal to the ground state. And now if you take functional derivative with respect to these auxiliary field, you will generate correlation functions of the system at 0 temperature. Now the second line is, okay, well, assume that there is a unique solution of this stochastic field equation. Well, then if there's a unique solution, you can change the delta functional to give the ground state by the fact that you enforce that the equation is satisfied times the Jacobian, which in this case is just the determinant of the second derivative of the bare action, the phi-4 action. Okay, so this is again true when there is a unique solution. And then what you can do, because you realize that when j hat is equal to 0, well, the integral of the delta functional is 1, so z in that case is 1. So you can, in that case, directly average the partition function over the random field disorder. Okay, so when you do this, well, there are a few standard manipulations to make the partition function a little more pleasant to work with. And this is done by introducing auxiliary fields. So for instance, the delta functional on the equation, you can just exponentiate the delta functional by using one auxiliary field, which would be a phi hat here, not phi, which is just the equivalent of the response field in the Martin-Tiguero's, for instance, dynamical formalism. Okay, so it's just standard procedure. Now you can do a little less standard, but procedure, which is exponentiate the determinant here of the second derivative just by introducing fermionic fields. So you have two auxiliary fields, psi and psi hat, that are fermionic fields. That is, they are anti-commuting fields. And again, you can exponentiate the determinant in this way. So in the context, for instance, of gauge theories and Fadeev-Popov theories, these are called just ghost fields. Okay, so we have now 4 fields. We have the phi field, we have the response field, which is a bosonic field, and we have the 2 ghost fields, which are fermionic fields. And the idea is then to introduce a superspace to describe all these fields by adding to the Euclidean space, to the d-dimensional Euclidean space, 2 Grassmann coordinates. So again, the Grassmann coordinates are anti-commuting coordinates. So they are different from the bosonic Euclidean space. And you introduce then a space combining Euclidean and Grassmann subspace. And you have this kind of supermetric that, for convenience, involves the variance of the random field here. Now you group all the fields that we had in one superfield, which again, lives in the superspace, that is, has coordinates, Euclidean coordinates and Grassmannian coordinates. Okay, and it's composed this way with, again, the physical field, the 2 ghost fields, and the response field. And from this, when you insert all this thing in the partition function, and the average partition function, what you end up with, you see, is a functional integral over now the superfield, living in the superspace, and with an action of the superfield, which has a part with the Laplacian, which is a generalization of the Euclidean Laplacian, but it's now the Laplacian associated with this supermetric. And you have a phi-4 theory, but now a phi-4 theory with the superfields. And here you can add super sources that are linearly coupled to the superfield. Okay, so this is just the phi-4 theory with the theories associated associated with the superspace. Okay, now what happens is that, again, because this phi-4 superfield theory is invariant under the isometries of superspace, so which mix together all the isometries of Euclidean space, the transformations of the subspace, Grassmannian subspace, plus an interesting supersymmetry that mixes Euclidean and Grassmann, which is a super rotation or super rotations, if you wish. And this is the important supersymmetry, really, of the problem for the Parisi-Sourlas construction, because you can show that because of this super rotation invariance of the action directly follows the property of dimensional reduction. And what dimensional reduction means is that, the critical behavior of the random field Ising model in d dimensions is the same as that of the pure Ising model in 2 dimensions less. So, for instance, that means that the anomalous dimension of the random field Ising model in d dimension is the same as the other anomalous dimension. So this is one property which comes from the super rotation and is equal to the anomalous dimension of the Ising model in dimension d-2, same for the correlation length exponent, and so on and so forth. And this can be derived, either perturbatively diagram by diagram or in a non-perturbative way. That's been done by many people, including us. And that property was found before at all orders of perturbation theory by Aroney, Greenstein, Young, and collaborators. And the beauty of the Parisi-Sourlas construction was to show that this whole business found in perturbation theory was in fact just a consequence of an underlying supersymmetry of the construction. This is beautiful, and I must say this is one of the most beautiful, maybe phys red letters that one can see. It's a 2-page letter, and there are no 10 pages of supplementary material. It's just written in 2 pages. So this is a real beautiful piece of work. But of course, one knows, and Parisi and Sourlas knew it, that it leads to a wrong conclusion, because the fact that there is dimensional reduction means that the lower critical dimension of the random field Ising model then should be that of the pure Ising, which is 1 plus 2, so that should be 3. But this contradicts rigorous result in D=3 by Imbri, Brikmont, Kupianen, that showed that there is a phase transition in D=3 for the random field Ising model at non-zero disorder or non-zero temperature. Okay, so that was the situation, and in some sense, it's a problem that it leads to the wrong conclusion, and what I would like to discuss is what is exactly the cause of this failure. Where is the problem? Well, there is one obvious drawback of the construction is that I said, everything is fine when there is a unique solution. Well, when there are multiple solutions of the stochastic field equations at 0 temperature, which of course is the case in the region of interest, well, then the Parisi-Sourlas construction, instead of keeping only track of the ground state, well, weighs all the solutions with the very strange weighting factor, which I wrote here. So instead of having only taking into account the ground state, so it's not what we would expect, you get something which you take the weighted sum over all the solutions with a sign here, which depends essentially of the number of unstable eigenvalues of the solution of the equation. So clearly, this is not the construction, or this is not the partition function that one would like to study. Now, there is another problem that actually was not considered in the discussion by Parisier-Sourlas and later discussions just after the paper, is that the construction also, as it is, misses singular collective events that are present in the ground state. So it's not only multiple solutions, but it's collective events present in the ground states, and which are known as avalanches or shocks, and which are associated essentially with the coexistence for some value of the external source of two distinct ground states. So it's exceptional coexistence, that are separated by this avalanche. So in a sense, there's no dynamic in the avalanche. It's avalanche in the ground state, but these are phenomena that are generically present in disordered systems because we are at zero temperature, and I will stress this more. So avalanches in the zero temperature equilibrium random field Ising model can be seen, for instance, and have been seen in simulations at zero temperature. Okay, so this is, for instance, one thing in the 3D model done by Liu and Damon a few years ago. And you see here, you're looking at the magnetization of the random field Ising model very near the critical point as a function of the external magnetic field. And you see, if you zoom on the curve, that it's a little jagged. And if this here is the zoom, so you see that, of course, because this is a finite size system, well, you have discontinuities, you have jumps. So you have abrupt jumps between ground states that takes place here. And this abrupt jump is what one calls avalanches. So if you're, of course, at small disorder strength, well, then you will have a macroscopic avalanche, which is, just a first order transition seen in the ground state. If you have a large disorder, then you will have avalanches, but only on small scales. And when you are at the critical point, well, what you have is that you have avalanches on all scales. And in a finite system, well, there's, of course, a cutoff due to the size of the system, and you will have spanning large critical avalanches, which will have a fractal dimension, df. And this fractal dimension will be important in what follows. So here is, for instance, a representation of a spanning avalanche near criticality from simulations. Okay, so what's the consequence of those avalanches that, again, are always present, especially at criticality on all scales at zero temperature? Well, to see this, then just look at a very simple toy model, which is a zero-dimensional random field Ising model. So I just consider one side. So there are no gradients, there is no interactions, there's just the potential. And what happens then is that the ground state, in the presence of, there's an external magnetic field, external source, and there's the random field, which will vary, of course, from site to site. And what you see is that you have a double well potential, and depending on the value of the source or the value of the random field, well, a ground state will be either on the left or will be on the right, and there will be one point at will they coincide. So when you plot the value of the ground state as a function of J plus H, so the sum of all sources, including the random one, so you have, of course, a an avalanche, it's a trivial one in that case, of course, because we're just not talking about collective effects. In that case, it's just a one-side effect. But you have an avalanche that occurs when those guys are equal to 0. And you see that the place of this avalanche depends on the random field, on the disorder. So how to keep track of this event, which again will be collective in D larger than 0, when you do averages over disorder. Okay, so for instance, when you look at pair correlation functions, well, it's not easy to find quantities that really have the signature of those guys. But you realize that you do this, it's interesting to take 2 copies of the system with slightly different sources, and to look at the correlation between the disconnected correlation, if you wish, between one sample where the external source is J minus a little delta J, one sample where the source is J plus little delta J, and you easily realize that the effect of this discontinuity in the ground state is to produce a something which should be of course even. It's to produce a singular term here in a cusp, if you wish, that is an absolute value dependence on the external source, okay, which is represented here. So we see a cusp, it's an angular point, but everybody says a linear cusp anyhow. And what happens is that the amplitude of the cusp is the second moment of the avalanche distribution. So clearly the signature of the avalanche is in the cusp. Okay, so how to keep track of singular collective phenomena is, after disorder averaging. So what we see is that we want to average. So we do not want to work with the disorder dependent free energy functional. We want to work with cumulants. But what is important here is that we need cumulants with different arguments. So we need to be able to take arguments that are a priori different and see if there is some non-analytic behavior when the arguments become equal. So when you take the sources equal. And for instance, in the toy model that was before, that I just showed here, well, in that toy model, it means that the second derivative, J1, J2 of this second cumulant, then has a singularity when J1 goes to J2 and has this cusp. And what happened is that the Parisi-Sourlas construction, you can show even in that zero-dimensional model, misses the cusp and then misses the signature of the avalanches. Okay, so what we did is that we wanted to revisit, not drop it, just revisit, just extend it, the supersymmetric formulas. So the first thing was to introduce the Boltzmann-like weighting factor with a small auxiliary temperature, so that you can weight the solutions in the generative functional with this Boltzmann weight. And this, of course, if the auxiliary temperature is very small, and in the end of all calculations, we want even to take the limit when it goes to 0, well, it means that this will properly select the ground state among all the solutions. Now, the price to pay is that you have to reformulate the whole superfield theory that you could do as before by introducing all these auxiliary fields. But now the superfield theory involves a curved Grassmann subspace. So the Euclidean space is still there, but then the piece which was with the two-dimensional Grassmann subspace has a curvature, and a curvature is just the inverse of the auxiliary temperature. But again, this is a price to pay, but it helps selecting the ground state among the solutions. And then, as I said, to keep track of the avalanches in disordered average cumulants, well, we need the full functional dependence of the cumulants, either the W cumulants, as I saw, or cumulants of, depending on the field, which are the one particle irreducible cumulants of the, obtained by the Legendre transform. And to do this, you need to introduce copies or replicas of the system, now coupled to distinct sources, as I did for the zero-dimensional case. And of course, because we are interested in critical scale-free behavior, well, the appropriate framework to study the cumulants in the superfield formalism is the renormalization group, which must be functional because, as I said, we need the functional dependence of the cumulant. And okay, this is reminiscent. This is the functional renormalization group has been used in a different context for disordered systems and interfaced in the random environment. Okay, so what's the outcome? Just in case I run out of time, it's interesting to discuss the outcome of what we did. And here is the phase diagram that we obtained in the dimension versus number of components of the random field ON model. So the Ising model is just the line here where n equals 1. So it goes from 2, which is the lower critical dimension, to 6, which is the upper critical dimensions for all those guys. And 4 is the lower critical dimensions for ferromagnetism for continuous symmetries, that is for n larger than 1. And you might have quasi-Lagrange order, but this is not what I want to discuss here. So what we find is that there is a non-trivial critical line in the phase diagram, with a critical dimension as a function of n, which separates a region where dimensional reduction holds from a region where dimensional reduction is broken. And of course, this region, encompasses the dimensions 2, 3, so it's low dimensions, so that of course it's what is found, also by rigorous results. So we recover the rigorous results where there is no dimensional reduction. And in this region, what happens is that the fixed point is still given by a supersymmetric, by the Parisi-Sourlas supersymmetric theory, which means that, for instance, if you start your flow, your functional flow, with an initial condition where you have killed some of the fluctuations, but not all of them, and your theory is not supersymmetric, well, supersymmetry is restored at the fixed point. So there is a restoration of supersymmetry in this region. And of course, it means that the avalanches actually are subdominant. In that case, on the other hand, there's a breakdown of supersymmetry, and it's related to the appearance of a cusp in the cumulants of the renormalized random field. Okay, so the way to do this very briefly is to use the functional renormalization group in the exact formulation. It goes from Wilson, Wegner, Polchinski, and more specifically the version given by Wetterich in the 90s. And the general idea is that you do progressive account of the fluctuations on longer and longer length scales, which mean smaller and smaller momenta in the relevant generating functional. And you do this by, adding some infrared regulator, which is some mass-like term that gives a mass to the modes of low momentum, smaller than some cutoff. So because they have a mass, well, then their contribution to the functional integral is very small, and you retain only fluctuations with wave vectors larger or momenta larger than some cutoff k. And that leads then, when you do this construction, to free energy functional that are cutoff dependent. So you have a whole family of k-dependent free energy functional, in particular the effective action or the Gibbs free energy of the one particle generating functional, all names for the same thing at the scale k. And the whole renormalization group flow is that you start from the UV scale where you have no fluctuations, so you're starting from the bare action. Then you integrate progressively the fluctuations, and you end up when k equals 0 to the full effective action. And this flow is given by an exact renormalization group equations that can be written down. And for instance, here, the details are unimportant because they will be always too little or too much, but you can do this in the superfield setting. So you have an exact flow equation for the effective action of all the replica superfields, that is a self-consistent, you see, but functional and with integrals. So of course, there's no way to solve this guy directly. And from this, you can just derive an exact hierarchy of functional renormalization group equations for all the one particle irreducible cumulants. So this is the starting point. So these are exact renormalization group, functional renormalization group equations for the cumulants. Now, of course, we need approximation. There's no way, as I said, to solve this infinite hierarchy. And empirically, the work has been done on this, not on the random field, but on the exact, but on the non-perturbative truncations of the exact functional renormalization group, is that the approach, in terms of effective actions, has very good properties under truncations. And of those who are interested, there is a nice physics report showing all the applications in different areas of physics that appear this year on this method. So what we do is that we have again, truncation scheme that allows us then to solve the equations. So we truncate the number of derivatives of Grassmann in terms of Grassmann coordinates, which is something that allows us to check how the ground state dominates indeed the physics, and what's the role of the auxiliary temperature or the renormalized auxiliary temperature. Then we truncate in the number of Euclidean spatial derivatives, because we were interested by the long distance physics. And we need to truncate in the number of cumulants, of course, keeping at least, of course, the second cumulant, because we know that the action in the cusp is there. And these truncations must be done in such a way that you do not break any symmetry, supersymmetry, and in particular that you do not break the Parisi-Sourlas supersymmetry in the limiting cases when it is valid. So what you end up with are coupled partial differential equations for functions now, not functionals, functions of one or several physical fields. And after introducing scaling dimensions, the usual stuff about renormalization group, you look for fixed points, you look at the flows, and you solve the functions now numerically for any value of d that you want. And here are some of the results. So it's solutions of the flow equations that are derived in the way I just showed. So the first thing that is important to note, and that we find, and as I said, this is something that we obtain by looking at the truncation of the derivative, the Grassmann derivative expansion, is that the renormalized auxiliary temperature flows to zero at the fixed point. So at the fixed point, there is indeed restoration of ground state dominance, even if at short scale, many solutions of the stochastic field equation can be introduced in the generating functional. But ground state dominance is restored at large scale. Second, what we find is that indeed there is a critical dimension. Here it's the random field Ising model, so it's near 5.1 plus or minus 0.03, depending on the level of the truncation. And we see that the second cumulant of the random renormalized random field has indeed a cusp below that dimension at the fixed point, and you see the cusp appearing nicely as you have renormalization group flow, and has no cusp, on the other hand, when you're above this dimension. So here, for instance, this is the second derivative of this guy, which blows up at a finite time when there is a cusp, and on the other hand, stays finite when you're above the critical dimension. Now, this can be seen also. This is still the flow, the functional flow. Now for the anomalous dimensions, and you can see that again above the critical dimension of 5.1, well, the two anomalous dimensions are always equal along the flow, meaning that the supersymmetry in that case is not broken, because the equality of those two guys is a consequence of one of the Ward identities associated with supersymmetry. On the other hand, here you see that after some time, meaning after some scale, well, supersymmetry is broken, spontaneously broken, and then you have two different anomalous dimensions. Just to give some general results as a function of dimension. So these are, again, the two anomalous dimensions. So eta bar, which is the one that controls the spatial decay of the disconnected correlation functions, eta that controls the spatial decay of the connected one. And you see that below that critical dimension, again, around 5.1, well, you see that above them, they are equal. So supersymmetry, the fixed point is supersymmetric. And below, you have a cusp, you have breakdown of supersymmetry, and the results are in fairly good agreement with simulation results by Middleton, by Martin Mayer, Nikolaus Fedas, and other people. Now, one question that was puzzling is that, why is there a critical dimension if, as I said, avalanches are always present at zero temperature? And well, the idea is that they are present, but they may be subdominant. And as I said, they have the largest one at criticality have a fractal dimension. Now, a heuristic scaling argument is, well, compare what's the total magnetization at criticality in a finite size system. So, well, it's given by, d minus the dimension of the field, which then is d minus 4. This one is d minus 4 plus eta bar over 2. And the idea is, well, okay, if the spontaneous magnetization is of the same order of the avalanche, then the avalanches are relevant for the critical behavior. If, on the other hand, the avalanches, scale with a lower dimension that the magnetization, then, well, they have no effect on the critical behavior. And this is this condition here on this fractal dimension on the avalanches. And you see that you can do the calculation at the upper critical dimension or in mean field. In d equals 6, well, the anomalous dimension is 0. So d plus 4 minus eta bar over 2 is 5. And in that case, the fractal dimension of the avalanches is 4. So you can check that at the upper critical dimension, indeed, the avalanches are subdominant. And indeed, there is a whole range that you can compute by doing a perturbation functional RG at two loop around the supersymmetric fixed point. You could see that there is indeed, this difference between the fractal dimension of the avalanches and the dimension of the total magnetization, which is 1, and then decreases as you lower the dimension. And so this is just the two-loop result, which goes to 0 at 4.6. And this is the two-loop result, assuming that there's a collapse of two fixed points that goes around above 5. And this is the non-perturbative result, which goes as 5.1 plus or minus 0.3. And this actually eigenvalue here has a nice physical interpretation that was, suggested a long time ago by Jim Setna, which it characterizes the number of critical spanning avalanches. So this number actually diverges with system size, like L to the lambda, at least when you are in this region above the critical dimension. So you have an infinite number of critical spanning avalanches above 5.1, whereas below 5.1, you have only one critical spanning avalanche. Okay, and this leads me to the conclusions. So the idea is that it is possible to extend then the Parisi-Sourlas supersymmetric construction to encode the selection of the ground state, well, at some cost, of course. That there is a domain of dimension where the Parisi-Sourlas supersymmetry is still valid, and in fact, this is again compatible with lattice simulations that show in 5 dimensions that supersymmetry and dimensional reduction are basically compatible with the numerical data within uncertainty. So this is very close to 5.1. The phenomenon is controlled, and this is an important, I think, aspect of the problem, because when you're doing the, this kind of, sophisticated and nice superfield theory in super curved space, well, it's nice to have a physical interpretation. And the physical interpretations, again, goes with the existence of avalanches, their fractal dimension, and their number as as a function of size. Now, just to mention, to conclude, that the formalisms of selecting the solution of a stochastic field equation has been used for other problems, including the problem of so-called Gribov copies in non-abelian gauge theories, and it's been done by Mathieu Tissier and co-workers in the recent years. And with this, I thank you for your attention.
Yeah, thank you, Gilles. I think Silvio has a question. I'm trying. Yeah, Silvio, you can go ahead and speak.
Hi, Gilles. Actually, okay, I have a couple of questions. Well, first of all, I wanted to know if the n equal to 18 that you mentioned, above which supersymmetry is restored, is something which is known rigorously.
No. Well, I mean, the answer is it is not known rigorously. Okay, there's, as far as I know, there's no rigorous work. It is known, it's a place, again, you can say it's 18 because you can do perturbative functional RG. So, there's a sigma nonlinear model, because this is the lower critical dimension of the ON model 4. So you can do a 4 plus epsilon perturbative functional RG at 1 loop and at 2
This
loops.
is the old work of Daniel Fisher, right?
Daniel Fisher started it. He never realized that there was the 18, the n equals 18 as was a problem, because he never solved these equations. He was interested afterwards by working on interfaces and depinning. But when you take the equations and you again continue them and you work a little more, actually, and you go to 2 loops, you find indeed that there is this point at 18. So it's the result of a nonlinear sigma model at 1 loop and 2 loops, but it's not a rigorous result.
Okay. The other thing that I wanted to ask, but there are 2 things. First of all, I mean, in one of your papers, basically you showed that these Caspi fixed points are associated to the fact that the replicon eigenvalue should be equal to 0. And I wanted to ask you some comment, especially because there are those results by Federico, Richard Senghi, Lenka, Florent, that in the random field Ising model, you cannot have a divergent spin glass susceptibility. And then the last question, and then I terminate, is what still is, according to you, an open problem? What are the open problems in random field Ising model? I mean, you seem to say that you have solved everything. So are there still problems, according to you? Are there still open questions or not?
Well, okay, thanks for the 2 questions, Silvio. Well, the first one is, indeed, there is no spin glass phase. Well, there's a rigorous demonstration, but there's no spin glass phase in the random field Ising model. What we showed with Dominique Mouana is that the instability for replica symmetry breaking at the level of the correlation functions, and the instability for the appearance of the cusp at the level of correlation functions appear at the same time. But again, you know, it's meaning that we have an eigenvalue of an operator. It's no longer like in the mean field spin glass, the fact that you have the spin glass susceptibility.
No,
It's an eigenvalue of measure zero, essentially. So what happens is that, yes, you have some sort of marginality in the problem, but if you wish, it is not in any susceptibility that you can measure. It's related to the fact, actually, that you have a cusp, and that if you take two derivatives of the cusp, you will have something that blow up. But this is not directly transposable to the existence of the spin glass susceptibility and the divergence of the spin glass susceptibility. So the two results are completely compatible. Now, your last question, well, you know, again, you would like, first you would like to have some rigorous results or you know, a certain results. You know, people still don't believe in the solution. You know, there's Slava Ryzhkov and co-workers put a paper on arXiv a couple of days ago, trying to find, you know, other ways, other approaches to explain whether or not there is restoration of supersymmetry as a function of dimension. Well, the nice thing is that he finds the same. That is, he finds that indeed there's a range of dimension where you have restoration of the Parisi-Sourlas supersymmetry. On the other hand, you know, the eigenvalue that they have that becomes relevant at a lower dimension. So in a way, our mechanism
4.9, right?
What?
It was 4.9 or something.
Well, it's 4.6 when you do Padé resummation, and it's 4.1 when you just do the loop expansion. Okay. So it means that you know, the avalanche mechanism would, you know, clearly operate before his mechanism. Now they pointed out some interesting features. You know, again, what happens at along this line, that you have the collapse of two fixed points, supersymmetric cuspless, that gives rise to one cuspy fixed point and not supersymmetric. And it's in terms of, you know, renormalization group theory, it's a very strange, very exotic behavior. And some of the properties, you know, in this phase or just at the critical point still, you know, would deserve, you know, I'm not sure physically it's super interesting to work in dimension 5.1, but will deserve more work to completely clarify, you know, the mathematics of the transition.
All right.
Thank you very much.
So are there other questions?
Shrikant, I have a short question.
Please go ahead.
So I was wondering about the Heisenberg case, n equals 3. And what would be the lower critical dimension for n equals 3 in the scheme? I mean, it's still 4.
Well, yes, n equals 3 is, I mean, this critical value here is also exactly known. It's 2.83 something. And n equals 3 then is above. And they actually, so 4 is the lower critical dimension. So there is no ferromagnetism in the random field Heisenberg model. There is no quasi-long-range order. And actually, there are some rigorous results showing this by Feldman or by Eisenman for the ferromagnetism that's known, and for quasi-long-range order by Feldman. Yeah.
Okay, and what about system of particles? I mean, original Larkin problem. Then when you have a system of particles and some random potential.
Well, the original one. I mean, in that case, they were really interested in the well, I think what amounts to be the same as the random as an interface, as a manifold in random environment. And in that case, it's the XY model that is interesting in that case. And you can show indeed, and that was shown by Jamarki and Ledoussal. You can show indeed that in that case there is a range where you can do actually perturbation expansion, where you have quasi long range order. But what we showed with Mathieu Tissier, and actually even at 2 loops, that's what we all found with Ledoussal, Viezo, and Mathieu and me, is that you have massive modes that actually arrive quite soon and that kill the quasi long range order. So even the XY case here has no quasi long range order, for instance, in 3 dimensions. Now, it doesn't resolve everything about the question of Bragg glasses, about all the questions of manifolds
Can be
in random environments, because this is only for the random field case again.
All right. If there are no more questions, thank you, Gilles, for your very nice talk. And I guess I would like to, I'd like, before I hand over to the organizers, I would like to thank all the speakers, Jorge Kurchan, Irene Jordina, as well as Gilles Tarjous, for stimulating talks and keeping to the time. We are finishing this session exactly on time.